Yeah, I'll share my screen.
Okay, while you're doing that, I'm going to introduce you so that we don't spend too much time on this. So it is actually my pleasure to introduce another early career spotlight, and it's Jaehong Yoon. And well, many of you probably might not know him, but you might know a lot of his work. So I personally cite quite a bunch of his works. He's done like lifelong dynamically expandable neural networks, has done a bunch of like continual federated learning that people are probably aware of. And more recently, he's done a lot of multimodal vision language models, like large scale models, which I believe is also what he's going to talk about a bit more today in the context of also continually growing embodied AIs. So again, it's a very deserving early career spotlight, and I'm very excited to hear the talk now.
Yeah,
Sorry.
me
And I
at
forgot to say
oh
he's at
yeah.
NTU in Singapore, and he's gotten his PhD from KAIST and has done a postdoc at North Carolina at Chapel Hill, which of course is very important. Sorry to interrupt again. Now the stage is yours.
Okay, yeah, thank you this kind of introduction. So, and I'm so glad to introduce my research vision and some part of my research to many researchers at CoLLAs. So as we can see that the title of my talk today is toward continually growing embodied AIs via selective and purposeful experiences. So I'll talk about some interesting directions that enable AI systems to continuously evolve by selectively learning from only the most beneficial experiences. And at the same time, these advancements beyond simply accepting the observed environments, but they can allow the agent to actively generate their own some customized environments based on their own goals and demands. We are living in the era of the data explosion or data flood, and we all know that the massive amount of the data are being generated every single day. So this rich and just collection of information, they form the very foundation for training today's most powerful AI models. Is how this trend has become even more significant in recent. So over the past few years, the data growth curve have stiffened dramatically. And this trend become further with data and benchmarks. So we see that submission have more than quadrupled in just 2 years, reflecting a surge in the data set and benchmarks in AI field. But this is just the beginning of the story. So even with current, the massive scale, the hunger for more data continues to grow. So what's driving this endless pursuit of more information? Many factors behind this. For instance, we usually compensate for the practical technical challenges, such as suboptimal training strategies or inherent architectural limitations, by simply scaling up data for training. But there's another current I'd like to focus on in this talk, is the world around us is constantly and rapidly changing. AI systems aren't just dealing with static problems or fixed past knowledge. They need to continuously adapt to ever-changing environments and evolving world knowledge. Just like the humans, we constantly learn from the new experiences and adjust to the world around us. So inspired by the human lifelong learning, the continual learning is a research field aiming for the progressive models. This is also essential for the real-world multimodal AI systems because it enables models to evolve in a dynamic and constantly the multimodal environments. Formally, it aims to tackle a learning scenario where the model that continually learn the multiple consecutive data sets over long time scales. So during training, when the model encounters new tasks, learning the zebra here, the model transfer previously learned knowledge to solve task problems. But we usually assume that the model loses access to past data, considering the several practical issues such as data privacy and memory concentrations. But this restriction on the data access critically causes under the knowledge. For example, when learning about the zebras, a model might override the previously learned features such as tiger prints or four legs in here by replacing them with the zebra prints and hooves. So as a result, it could forget some kind of the essential knowledge of the pre-trained models from the past tests. To address this, many recent work have focused on reducing these forgetting issues while progressively enhancing the model's capabilities. As an extent, I've recently been interested in bridging conventional multiple modalities. So we can enable models to adapt across diverse inputs while retaining the past knowledge. So with multimodal large language models in the forefront, there's still the best potential to extend and apply them more broadly to real-world scenarios. Although the idea of the continual learning is highly attractive and there should be some multiple exciting extension to the model, sometimes it has critical gap to directly apply for the real world. So which limits its practicality across the various realistic domains. So for example, one, I'd note that unlike the traditional continuing assumptions, the large-scale multimodal, the real-world data accumulates over time and remain accessible rather than being encountered in the isolated tasks. So in practice, we continually deal with an ever-growing pool of the open source or accumulated data set. The challenge is not sequentially, but dynamically prioritizing the most critical information for ongoing training. Others is reframe the problem of the continual learning through the lens of the continual data selection. So let's describe the problem statement step by step. Assuming an ever-growing pool of training data, the new public multimodal data continually released and incorporated into a data pool. However, they may include a large amount of the undesired type of inputs, which degrade the task adaptations and forgetting to a much larger degree. My prior iClear 2022 work, online course selection, explored filtering out such undesired training samples in an online manner for the vision-based continual learning. Here, we leverage the sample diversity and relevance, as well as some affinity to the replay buffer, which is guided by the gradient level momentum of incoming samples. This work, we can say that we generalize this idea for much more the realistic and multimodal settings. So formally, some score, like the entropy, perplexity, EL2N, and so on, so we identify the data points that are most beneficial for further improving the current model. And train the model on these, obtain the 10% amount. So this continual cycle of selection and learning allows the model to remain efficient and adaptable as new data or the training that becomes available. However, these highlight the two additional key challenges. First, how do we effectively sample the data to learn? This is a non-trivial because they contain very diverse multimodal tasks and continual changing degree of the data imbalance and their distributions. And the second, the two will be the how do we tackle the endless growth of this ever-growing data pool? As the data pool constantly expands, the processing all multimodal samples becomes increasingly expensive and also impractical. In the first aim, how to sample the data to learn, I introduced one interesting observation that there's no single metric universally works. So relying on one important score cannot address all kind of the diverse multimodal tasks or domain categories. So on the left, we see the distribution of the EL transfers across the various visual language tasks. And as shown in this plot, the higher EL2N scores are more common in some tasks like captioning, but it generally shows a lower scores in the knowledge QA. Ignoring this can lead to biased sampling, which can cause the model to overfit to frequently selected tasks throughout the selection and learning cycles. On the right, we see a similar trend in scores, where each task also has its unique patterns. In short, different tasks benefit from different important metrics. So for the task-specific sampling strategies, in response to constantly evolving the model's knowledge and the changing data distributions. One interesting observation is that the recent data selection function, the mostly assumes a single modality processing. So that means it overlooked the potential entanglement across different modalities. For example, only the confidence the VLM's output, as shown in this the plot. The x-axis denotes the score, and the y-axis is the sample diversity, the sample density. So this is useful for judging the output, the naturalness of the text outputs, but not for assessing how well it connects with the visual inputs. So we propose image grounding scores, the multiple selection. So here, perplexity between the only and the image query input. So a higher IG score, higher image grounding score indicates the model relies more on the visual contents, like the reading a text in an image, while the lower suggests that image is unnecessary to make the correct answers. Building on our insights, we developed the Depth Infinity, an efficient and continually evolvable multiple logic model. This approach aims to select the informative samples using the various selection strategies in a combinatorial manner. At each time step, a new data is integrated, and we allocate the entire data in the pool into a pseudo-task clusters. And next, we select influential samples from each cluster for model training. Motivated by our the previous observation, we propose a new multi-way data selection approach. So it automatically chooses the best scoring for each cluster based on their discriminativeness. This is measured by the entropy scores for each the clusters. So we can ensure a skill set of highly influential samples from the training pool. We then train the models on these adaptively collected data sets. On the other hand, as we discussed in the second challenge, when the data grows, computing scores becomes costly. So to manage this, we additionally propose the permanent data pruning. So in here, we calculate the pairwise cosine similarities between the samples within each pseudo cluster. So we can remove the redundant samples while maintaining its diversity. In the end, we ensure the controlled and measurable growth of the training data pool, even during the long training period, and integrating the very extensive scalable data sets in our original entire training pool. All right, so for training, in addition to Lava 65 instruction data set at the initial stage, where the t is equal to 0, we consider the following order of 5 popular visual instruction data sets are integrated into our original data pool. So the pool continuously grow and grow and grow. And on the left is the benchmark that we made across the various skills, BQA, multilingual understanding, grounding, and reasoning, and so on. And as shown in this result, compared to the existing the data selection methods, our approach achieves the higher overall accuracy while significantly reducing the degree of the forgetting. So which demonstrate both strong performance and the stability during the continual the multiple learning through our proposed multi-way data selection and additional, the multimodal focused, the selection, the important scores. Okay, and let's move on to the next chapter. As said, we enable AI models to continue to learn and adapt to expanding data over time. However, as this chart shows, data scale for training will soon converge the total of the data on the internet. Similarly, in 2024, the co-founder of the OpenAI, Ilya, goes, there's only one internet, emphasizing that the factor for future AI will be the data. And I believe the key challenge now isn't just having the more data, it's about having the right data. We need to focus on finding high quality, purposeful data that directly addresses the problems users really cares about. This insight bring me to the next research direction. In short, I focused on addressing this challenge by adaptively generating the training sources. So multimodal models achieve more diverse and meaningful learning experiences from such synthetic sources during their training. That direction, I recently report the embodied to relevant simulation work. So here, the agents autonomously explore the simulation works, acquire diverse skills, and make the novel discoveries. So we start with the basic tasks for survival skills, gathering resources, crafting tools, and hunting zombies, and progressively master the advanced strategies or achievements or skills within the game's tech tree. Recent initial trial or recent work directly employs the large language models as a decision-making agent for reasoning, planning, and executing actions in the environments. However, this leads to heavy computational demands and excessive processing time. For instance, when we assume that crafting a pickaxe in Minecraft, we require the multiple prerequisite steps, like the collecting wood, placing a table, and each of them triggers multiple sequential large language model query. So these frequent queries and frequent sequential queries slow down the execution and increase the cost. To enable much more efficient decision-making to these continual AI models, we need to minimize this unnecessary large language model cost while maintaining the intelligent behavior, which is especially important for the complex skills requiring the multiple prerequisites and environmental adaptation. And we thought, can we create the adaptive training environments that really help reinforcement learning agent focus on learning certain skills where it's at the most? So building on this motivation, we developed Engine, a method that uses the large language models to dynamically design the learning environments for embodied continuous learning agents. By analyzing an agent weakness and adjusting the training conditions, large language models can create an adaptive curriculum that helps agents acquire skills in a progressive manner. In the end, by imagining and exploring such tailored, customized environments, autonomous learning can progress beyond its past experiences during the continual learning lifespan. Specifically, we first provide a large language model with a prompt composed of some several components to build environments. And here we include the feedback from the previous cycle, and which we will be discussing later. And next, large language model generates adaptive and custom environment configurations. And these configurations can be inverted into the simulation worlds for this training framework. And then the next step is the training on these customized environments and assessing its achievement. So first, the RL agent is trained in these generated environments tailored to help the agent improve the certain skills or achievements which it struggles. And once trained, we evaluate its performance in the basic environments. And after training, we can collect the evaluation results, and these results are provided back as a valuable feedback. So we can adjust the training environments to better target the underdeveloped skills and less focus on certain skills that the models already works well or already familiar with. So by looping this process multiple times, the agent progressively improves using the targeted and adaptive skill training. For evaluation, we use the Crafter benchmarks that features 22 different achievements. So the agent can unlock during the play episode. Gems are definitely can be easily unlocked in a few steps, like collecting wood or collecting saplings, such as making iron pickaxe or collecting diamonds, requires several prerequisite achievements to be unlocked. As shown in this plot, where the blue curves represent a baseline PvP model trained on the original Crafter environments, our engine enables more accurate and stable learning of the complex skills. So for instance, MGen required fewer training steps to craft the stone and iron tools with the lower performance barriers. So that means we make the agent to learn much more faster and stable without our cost or some computations on random traversing. And okay, yeah, this illustration additionally shows that how MGen progressively adapt the training environments to strengthen the undertrained skills. As shown in this result, in these examples, if an agent struggles with the collecting core, and the next cycle, we introduce the mining-focused environments, making the relevant skills much more intuitively and easily. So in the end, the agent trained with the MGen, which is represented by the yellow bar, significantly outperforms the PPO baseline, which is represented by the blue bar. And now we see that the model is still struggling with the make test. So if the crafting tool remains a major challenge, MGen autonomously provide us some environment configuration, which can be easily to learn the making stone pickaxe. For example, we can easily adjust it to provide some key resources to make the iron pickaxe, the stone pickaxe. So this environment configuration doesn't learn faster and improve the learning those skills and efficiencies over the successive cycles. And in the end, we see that our model shows some much significant improvements the handling those some very challenging skills compared to the basic our agent training. In addition, we also evaluate our approach on the haste benchmark as well. So in these environments, agent must successfully find the gem, the nice gem, after navigating a maze and opening all colored locks in appropriate orders. So as shown in this result, our MGen trained the models much higher scores with the higher reward, which represent that we can much more easily and appropriately focus on the handling the complex skills or environments to make the certain achievement. All right, so far we've explored how the model can only carefully select the inputs and expand the model's capabilities beyond the past experiences. And this can be done by integrating the adaptively generated data environments. This feedback-driven approach helps the model evolve with an ever-changing multiple environments and making these AI more flexible, scalable, and generalizable. Now, to briefly share several future and going directions I'm interested in or I plan to pursue. So I'm eager to build continually adaptable embodied AI models that they can react appropriately to the unpredictable environments and diverse user needs. So such actionable embodied AI should look from not only from the surroundings of the real world, but also can from the retrieved information from external database along with some other knowledge sources. And at the same time, the multi-agent cooperation could reduce the knowledge boundaries of single agent. So this agent can be assisted by the indirect experiences from the other continually adaptable agents or the media. So these capabilities will be a key innovation towards some home assistance, industrial, rescue, or educational robots, which can be a broad extension of these continual applications. In addition, the recent insightful discussions of embodied agents and Google Genie tree also highlight the rapid progress in world models that perception, action, and memory. I'm interested in this direction as well. So the next step is to develop the continuing agent that live and evolve within these worlds. So it can be the much long-term memory, adapting strategies, and long-term goals and reasonings over the past experiences to make the models much contain the broader or targeted experiences and knowledge or some capabilities to handle such kind of certain tasks or some challenges. And at the last, as we push toward the truly autonomous continual AIs, but we ignore one important thing. So the one important thing we need to keep in mind is that, in real, many web collected and synthetic data set contains very untrustworthy or unethical contents. And this critical risk should be addressed before scaling the continually adaptable multimodal AI. Because, when these flowed data sets integrate into the learning systems, the continual learning systems, the AI doesn't just observe those biases, but it amplifies them over time. So this creates a very vicious cycle. The models keeps learning, absorbing more biases, and gradually becoming less trustworthy. Therefore, the next generation of the continually adaptable multimodal systems or environment must be not only powerful, but also responsible, fair, and aligned with the human values. So we can ensure this new knowledge along with the ethics and safety while becoming more and more intelligent over time. So this is also especially critical in multiple high-stake applications like the healthcare AI, various embodied AI domains or applications, and AI for sciences, where the unreliable decisions can result in very serious consequences. Yeah, in the end, I'll be valuable by combining those reliability and the safety to the various continuing applications. And in this way, I believe we can create the agent that not only continuously evolve the imagination and interactions as we introduced in our previous slides, but also do so with the consistency and coherence. So throughout the operational lifespan, we can really grow with those kind of this the embodied agent or the intelligence. Then yeah, that's the all for my presentations, and thank you for listening. I'd like to express the acknowledgement to all my collaborators for this work. And if you are in my work or like to dig further, so please feel free to check my personal website via this QR code, or you can easily reach out to me by email. All right, thanks so
Thank you. We started a bit late, so we're gonna have time for like 1 or 2 questions still. So if anyone has a question, like raise your hand again, as usual. Okay, there's an awkward silence. I'm gonna ask one question to you. So my question is like a lot of the stuff with the LLM prompts, like you said, is really computationally expensive. Do you think the only way to like reduce this computational expense is just to select like more clever data? Because I feel like that's a short-term solution in like the next 2-3 years, but eventually you're just gonna get that same compute boundary hit again. Like have you thought about making the process itself more computationally cheaper?
Yeah, that's the major bottleneck in near future, and it's also the major bottleneck nowadays. So that's why I'm investigating on how can we calibrate the most beneficial information that the model additionally require. So not only the simply accepting the all knowledge in the single the huge models and retrieve all the things from those some very heavy processing, but we can modularize those knowledge and we can modularize the models to achieve some very targeted information. So we can easily handle these because not all models in our user cases to all models or kind of the knowledges. So it is very important. How can we efficiently storage or connect certain type of knowledge or some information to the works? So this is very highly aligned with the recent advancement in the multimodal reasoning. So not only for using the huge models, but also focusing on the how can we leverage the multiple agents very combinatorially, or how can we decompose the very dense information to some sub-steps so we can adaptively employ those kind of some sub-steps based on the user requests, user requirements. I believe those kind of some decomposition or modularization should be one of the key future directions that we can further address. We can further address those issues very efficiently.
Thank you so much.